Okay, so here's our goal today. You guys can read from the topic. Our goal is to measure electricity. Okay. Now, before we talk about how to measure electricity, we should really talk about what electricity is. And I don't know if you guys noticed, but I actually skipped a question on the assignment. Maybe you answered it already, but question number 4 on that assignment right here was describe what electricity is. And I skipped over that one on purpose because really that's where I want to start with today's lesson. I want to describe to you what is electricity. You guys all have heard of electricity. I mean, you've used the word a lot before, but we need to actually describe what is it. Not what does it do, but what is electricity. So I want to give you guys a bit of a history lesson before we start. We've already done this in chemistry. Rutherford, it was 1909. He made a very, very important discovery with that gold foil experiment. He realized that there is a nucleus. Okay? All of the matter in an atom is shoved together here in the nucleus, and the electrons are around it. Okay? Before that thought, Thomson had an idea of how matter worked. Thomson believed that all matter was like a ball or so, and inside were little negative bits, kind of like raisins in like a muffin or chocolate chips in a muffin. He actually had a name for it. He called it the plum pudding model. That's what they used to believe. And they believed that the electrons were internal. You guys know what internal means, right? Like inside? Yeah. Okay. Well, Rutherford had a brand new idea. Rather than the electrons being on the inside, Rutherford had a hypothesis that all of the protons and neutrons were in a nucleus and the electrons were on the outside. It's subtle, but it makes a huge difference. Here, the electrons are inside. Here, the electrons are outside. But here's what this means. If the electrons are outside of the atom, kind of like we now do believe to be true, it means that electrons can be gained or lost. You can add more electrons or lose electrons. And we've already used that terminology in chemistry. We use the word ion. And if you guys recall, the way an ion works is either you gain more electrons, and if you gain more electrons, you become negative, or you lose electrons, and if you lose electrons, you become positive. Does that make sense? And really, it's because of Rutherford's internal idea of how you can gain or lose electrons that we can now start to talk more about electricity. And I want to talk first here about static electricity. When an object has more or less electrons than it should, but it's just sitting there, it's static electricity. And I showed you guys this yesterday. Remember when I had that cloth and that black rod and I rubbed them together? That was static electricity. Okay, where I was taking electrons off of the piece of fur and I was attaching them to the black rod. Okay? That's static electricity. Static meaning that it's just accumulated. It's just sitting there waiting to be used. And often, static electricity, the word we would use is it discharges. And I'm going to show you that on this picture right here. Discharge. Anybody ever gotten a zap before? Like just a mild little shock? That'll work, yeah, trampoline. I'm gonna. Ooh, that is actually a little less safe. Yeah, don't do that. Ooh, that could be way dangerous. I'm actually gonna show you guys in our lab on Thursday. Shh, sit up, guys. I'm gonna show you in our lab on Thursday some examples of static electricity when we start. But have you ever gotten a little mild zap? I mean, the classic one is that you've got your feet on carpet with socks, and you shuffle your feet, and then you go zap your buddy. You ever done one of those before? Yeah. Boy, you do some risky things here. Wow. Okay, now here's the point I want to make though about static electricity. Static electricity is actually not moving. It's actually stationary. Guys, focus again, please. Now, although you might get zapped, focus. Static electricity, it might discharge. You might have a whole bunch of... Oh, I can't even see that color. Let's try a new color here. Let's try yellow. You might have a whole bunch of extra electrons on your finger, and they're going to zap away to a piece of metal. It may discharge the electricity, but it just happens once. It's not like there's a continuous loop or circuit. Okay? I've got a picture here of lightning. People don't actually necessarily know this, but lightning is actually not electrical current. It's actually static electricity. What happens when lightning occurs is a whole bunch of negative electrons start to accumulate on the bottom side of a cloud. And a whole bunch of positive charges then accumulate on the top of the cloud. And so you get all of these negative electrons right here. Well, eventually there's so many electrons, there's so much of a buildup that a discharge, that's the word we use, a static discharge takes place. And those electrons will zap into the ground. Does that make sense? And it's almost like that ground wire idea again there. The electrons are going to try to find their way back into the ground. But once the lightning strike takes place, that particular lightning strike is done. Okay. Now another cloud might strike lightning, and it might build up more charge again, but it was like a one-time thing. Okay. That's static electricity. It just discharges once. When we talk about, though, electricity in general, I'm talking more about completing a circuit like we did way back in a picture like this. The way electricity as like a circuit runs is it comes from, say, like a transformer. It goes through the hot wire. It runs a device. It loops back and goes through the neutral wire, and it keeps going in a never-ending cycle. Does that make sense? Now, if you're talking about electricity as like a current, a consistent current, then it has to go in a loop, and you have to continuously have wires running in a loop. And if you ever break one of those wires, like say when the fuse breaks, well then the electricity turns off. Okay. However, static electricity is different though. Static electricity is a one-time zap. Does that make sense? The electrons are not going to then run through this, go all the way back around, and just like keep circulating. Okay? If it did that, we call that electrical current. Which, where was I going with this one? I guess I'll leave it on this slide right here. Do you guys feel like you get that idea though? Static electricity, buildup of charge, and eventually that charge is going to like zap somewhere else. Current, or electricity that we use in our devices, which we're going to get to, it runs through a constant loop. It'll keep going in a cycle around and around. Now, one of the things I want to talk about in this slide right here leads to the next one here. You guys might already know this, but when we were watching that little, you know how those little two leaves were separating there? We were actually witnessing electro principles, which are these. If you have like charges, they repel each other. The word like in math and chemistry and physics, the word like means like the same. You guys ever heard that word before? Yeah, well, not the same, but like. Have you ever heard how like means the same? Sure, that'll work. Yeah, like terms in math, yeah. So if you have two positives, they actually want to go away from each other. If you have two negatives, they also want to go away from each other. But if you have something that's opposite, like a positive and negative, they actually attract. And this explains why in that little demo I did yesterday, remember how I had that little box there? There was that little metal ball at the top, and then there were those leaves in the middle here. And how those leaves, they separated. The reason why they separated is that this leaf became negatively charged. This leaf became negatively charged. And when they're both negatives, guys, shush. When they're both negative, negative things want to get away from other negative things, and they try to separate from each other. That same logic is actually what's happening in this lightning cloud right here. There are so many negatives being built up right here that they actually want to get away from each other. And these negatives right here are actually being attracted to the positive ground. And so eventually what happens is these negatives decide to, like this negative right here is kind of sick of that guy right there. So it's going to try to leave. Well, this guy is going to try to leave too. And this guy's going to leave too. And eventually it makes like a lightning bridge. It makes a pathway where the lightning can zap. And it's really based on this principle. Similar things go away from each other. And opposites attract. We actually see the same principle in magnets. You guys used magnets before, right? You take two magnets, you try to put them together, they like cling together. Because what you've really done is you've taken the north pole of a magnet and the south pole of a magnet, you put them together. You flip the magnet around, and now you try to put them together, and they don't go together because the opposite sides are next to each other. Very similar concepts here. Okay. I've got a whole bunch of pictures over the next few slides kind of describing some illustrations of some of the activities we've done before. This one here is actually a classic one. You ever done the whole rub the balloon on your head and then stick it to the wall? Now, what ends up happening if you ever try that one here is that the balloon takes all of the negative electrons out of your hair. And so the balloon becomes very negatively charged. And then as soon as the balloon becomes negatively charged, the wall... Guys, focus please. So much ambient noise here. The wall is positively charged. What ends up happening is that negatively charged balloon can then stick to the wall. Let I mean, here's another picture kind of illustrating the same thing. If both of these two little pendulums, I guess, are positive, they would go away from each other. If both of these things were negative, they'd also go away from each other. But if one was negative, one was positive, they'd actually suck back in together. Like I said yesterday in our lesson, 200 years ago, that would have been considered like magic and sorcery, but like we don't think of that anymore. Like magnets are known nowadays. We know how this stuff kind of works intuitively. Okay. What I'd like to show you here is a really important term. I'm actually going to use it in our lab a lot. It's called separation of charge. I'm going to bold this here. Here's how separation of charge works. Yesterday, actually, you know what? I'm going to grab the same device again. I'm going to show you again because I want it to be sitting here. Give me a second here. Where did I leave this? Here, I'm going to use this thing one more time here because it's worth it to be able to visualize again. Okay, right now, this device right here, it's neutral. Okay. And what I'm going to do is I'm going to provide some static electricity to this rod right here, and you can even hear it. Like, be quiet here. Listen carefully. Can you guys hear the little, like the little electrons moving? Not the rubbing, but you probably can even hear the little electrons zapping. Okay. Now, as I bring this close, we saw yesterday it caused the leaves to move. Okay. Here's what's happening. It's called a separation of charge. It's kind of similar to this picture, only on a smaller scale. If I bring this negative rod really close to the object, all of the negatives leave. Why? Well, if this is negative, negatives won't want to be by other negatives, and so the negatives go to the other side as far away as they can. So in this picture right here, can you guys see how all the negatives went to that side of the sphere? Well, like things try to get as far away as possible, but that means that the unlike charges, the opposite charges, they're going to attract. So all the positives are going to come to this side right here. That same principle is happening here. Let's try to describe this again. This is very negative. I'm going to bring it close. The reason why the leaves separate is that all of the electrons inside this device right here, they're trying to get as far away from this guy as they possibly can. And since I'm putting it up top right here, the electrons are getting pushed down into the bottom. Does that make sense? So what's really happening here is this sphere right here is now positive, and the leaves are both negative. But if both leaves are negative, if this leaf is negative and this leaf is negative, what do negative things want to do next to each other? They want to repel each other, which is why they start pushing each other away. So what we're really seeing right here, if we could like zoom in, you guys ever watch the Magic School Bus? My daughter watched Magic School Bus. If we went on the Magic School Bus and we like zoomed in right here, what's happening is this is negative. The ball right here is becoming positive. There's not nearly enough charge on here. The ball is becoming positively charged because all of the electrons are going as far away as they possibly can. And once they go as far away as they possibly can, when both leaves are negative, the two negative leaves want to separate, and they want to spread out as far as you possibly can. Specifically, this happens more with girls. You ever have like staticky hair? Been there before. Okay. I have 3 daughters. I'm gonna know what this is like. Similar concept here. The reason why your hair gets so staticky is that your hair gets a lot of electron buildup on it. Well, this piece of hair that's got electrons on it, listen. You're not listening to me. Okay. This piece of hair that has electrons built up on it, and this one, and this one, and this one, they all have electrons. But the negative charges do not want to be by each other, and so they go everywhere, and they spread out as much as they possibly can. If you've ever seen a picture... Am I wasting my time here, guys? I teach 5 lessons. Okay, all I'm asking is your best attention, okay? I don't think I'm that bored of a teacher. I'm trying to explain this to you guys, but you're so distracted. You gotta be able to focus. What ends up happening is your hairs, they end up all picking up electrons, and they like go everywhere in the same way that these 2 little leaves are like a piece of hair. When they both get negative charge on them, they want to separate. Right? And so you have to try to find a way to like remove that sort of cling. Okay. The word I want you guys then to know is called separation of charge. It's when you bring it close but don't touch. Okay. I've got a lot more pictures here just to kind of describe the same concepts. This is, again, building up static electricity. Here you've got, I mean, the exact same thing I was just using. You've got your plastic rubber rod, and you've got your fur pelt. And what ends up happening is when you rub them next to each other, all of the electrons come off of here, and you get more electrons on here. So it becomes very negatively charged. Okay. It involves separating the electrons through some sort of friction. Okay? There's now charge right here. Take a look at this item right here. If something was neutral, how many electrons to protons should there be? If it was neutral, they should be the same. Does that make sense? If there were 5 electrons and 5 protons, it would be neutral. But now that we've charged this, look at this. There's 1, 2, 3, 4, 5, 6, 7 negatives to 1, 2, 3, 4, 5 positives. Yeah, so if you're going to make something negatively charged, you're adding more electrons to it. Does that make sense? When I am doing this right here, what I'm really doing is I'm taking electrons from here and I'm adding them to this guy right here. So there used to be 50 electrons and 50 protons. Now there's 55 electrons and 50 protons because electrons went from here to here. Does that make sense? Yeah, what ends up happening is this guy actually sometimes becomes more positive. Because really, if this guy here is gaining electrons, this one's losing electrons. The problem here, though, is that pelts and furs, they actually usually pick up so many electrons along the way. Like clothing will build up static electricity as well. So this guy actually probably already had lots of electrons extra as it was. So this thing probably isn't neutral, actually. This thing has lots of electrons, and we're just adding some more to here so that we can do things like that. So the word we want to use then is if we bring, I need to go back a slide, sorry, don't change this yet. If you bring this really close and do not touch, the word we use is induction. That's way too light to see. I'm going to write it better here. The word we use is induction. Induction involves bringing it really close, but you do not touch. Do not touch. And what ends up happening is if you induce something, it causes the electrons to move to the other side and the positives to move to this side, and you get this separation of charge. That's called induction. Here's the thing about induction, though. What happens when you move the rod away? Well, it goes back to normal. Right? Here it was, equal balance of electrons and protons. You bring the rod close to it, all the electrons go to the other side, all the protons come to this side here, sure. But do you guys see how it's still 5 and 5? Take the rod back away, what happens to this thing? Well, it goes back to normal. Let me show you that with this one more time here. Okay. So ideally this is a neutral rod, and I'm now going to charge it, giving it static electricity, by taking extra electrons off the fur and adding them to here. If you look close, you might even be able to see that some of the hairs on here are literally standing on end, kind of like when your hair kind of stands up a little bit. You can actually see the hair standing on end. When I bring this close, it causes all of the electrons to go down to the bottom and the protons to the top. Okay, but here's the key thing here, guys. When I bring this close, yes, it separates. Ooh, it actually touched. One of these hairs on there touched. When I bring it close, it separates. But when I take it away, it goes back to normal. Does that make sense? That's how separation of charge works. This is called induction, bringing it close and separating it. But on the next slide I have right here, I want to talk about something called conduction. Conduction on this slide right here is when it actually, you touch, you transfer. Remember how this guy had a whole bunch of extra electrons on it? Well, when I actually touched the object right here, all of the electrons that were on here have now started to go onto there. And so there were like extra electrons here. I've moved them from here to here, and now I'm going to move them from here to here. Well, now the leaves stay separated because this whole thing right now has extra electrons on it. When I move it away, it's not like it's going to come back again. You know what I'm saying there? So induction involves going really, really close, but not touching. And it causes all of the negatives to go as far away as they can, and the protons to stay close. But as soon as you move your charged object away, it just goes back to normal. Conduction is kind of like this picture right here. Imagine that you have a whole bunch of charge on this guy here and none here. And then they touch, so you bring them together. Well, now, a whole bunch of these guys right here are going to move on to this one right here. And when you separate them away, well, now they're both charged. And it stays that way. This one right here, if I go back a slide, when I bring it close, it separates, sure, But as soon as I take the rod away, well, it just goes back to being neutral again. So let me define that for you one more time. Induction involves bringing something very, very close but not touching. Conduction involves actually direct contact. Conduction is going to be permanent, whereas induction, the phrase I want you guys to know, separation of charge. It separates temporarily. What I've got next here is a whole bunch of pictures. Oh, here I finally have the word induction written down here. I thought I did. Here's the word induction. And again, I want to kind of show you the same concept here on the slide, then we'll move on. The way induction works, bring this negatively charged object close, but do not touch. All of the electrons are going to go way over here, because electrons hate being by other electrons. All of the positive charge will build up over here, and you'll have a separation of charge. Now, one of the cool things you can do then is if you know how to separate charge, you can make charged objects. And I've got some pictures here to show you the idea. So see that you can follow along with what's happening in these photos. Imagine that you bring a positive rod near this ball right here. What's going to happen? Well, all of the negatives are going to come to this side because negatives want to be by positives, and all the positives are going to go far, far away. Now imagine what you do is you attach a ground wire. So what we're going to do is we're going to attach a little wire, and this is the symbol for a wire that goes into the ground. Well, what's going to want to happen then is electrons want to be on this side right here, right? We want electrons right here. Now, normally, a lot of electrons go into the ground, but we could actually have electrons come back up from the ground, and more electrons could come up through this wire so that even more of them could come over here on this side right here. Well, then when you remove the ground wire again, well, then it just goes back to being, actually what they're doing here is they're cutting the ground wire. And what ends up happening is when you cut the ground wire, all of a sudden electrons have come up through this wire. There's more of them on here than there were before. And now you can see in this last photo right here, now there's actually an extra electron. There used to be 3 electrons and 3 protons, but now there's actually 4 electrons because extra electrons came up through the ground because they wanted to be attracted to this positive rod. Yeah. Yeah. Yeah, you could have a positive or a negative charge, actually. Here's another photo here. Here I'm bringing a negatively charged object nearby. Actually, let me talk about that point for a second here. Joyce, how do you get a negatively charged object? You give it more electrons. Does that make sense? How do you get a positively charged object? Not more protons. Take away its electrons. Does that make sense? Go back to Rutherford's model. The protons are stuck in the nucleus. You can't move them. But what you can do is you can get rid of electrons. If you add more electrons, you're negative. But if you take away electrons, you're positive. So that's how you can become positively charged. Remove its electrons. Here's another kind of scenario here. Say you take a negatively charged object, and I'm going to bring it really close to this guy right here. Joyce, this will actually show you how you make a positively charged object. I'm going to bring this negatively charged object super close to this guy right here, but I'm not going to touch. Well, all of the positives will want to be by this side right here. And all of the negatives are going to want to go as far away as possible. Let's say the negatives actually have a ground wire here. The negatives are going to start going through that wire and go far, far away. Let's say you now cut that wire. All those electrons, you kind of like shove them far, far away. Like say you put them on a rope hanging off of the end of a cliff. And then you cut the rope. Okay, I know it's kind of a sadistic metaphor here, but hopefully you get the idea. Well, now all those electrons are lost. They're now stuck way over here. And what you're left with is an object where there used to be negatives right here, but they went down the rope, and there's actually all that's left is positives. Does that make sense? So that's actually a way that you can make a positive charge. Bring a negatively charged object near somebody that's neutral. All of the well, kind of, yeah. All of the positives come close. All of the negatives kind of push them down the rope. So all the negatives will now start going as far away as they can, because if you bring a negatively charged object nearby, the negatives want to get away as far as possible. Then cut the rope. Well, now all the negatives are lost, and all that you have left are positives. Now you've created a positively charged object. That's called induction. You didn't actually touch anything. You just induced a charge. Okay. And then this is kind of my last picture on this topic here, where I've shown you this using the electroscope. So when you bring the positive or negative charged rod nearby, it doesn't matter which charge it has. If you bring the positive nearby, all the electrons come up to the top, and then the bottom becomes positive, and so they repel each other. Or you bring a negative right here, all the electrons go down as far as they can go. But again, negatives want to repel each other. Does that make sense? I think this is more pictures of the exact same sort of thing here. Maybe I'll move forward here. Okay. Everything I've been describing then up till this point here has been static electricity, where there's a buildup of charge, a one-time buildup on an item, where if you want to become negative, you gain more electrons. If you want to become positive, you lose electrons. But that's actually not electricity, that's static electricity. Let me say that one more time. When I'm playing with stuff over here, and I'm rubbing the fur on the plastic and I'm touching it to the thing there, that's not electricity, that's static electricity, a one-time buildup of charge. For it to be true like electrical current, it actually has to flow in a pathway. And that's what I have as this definition right here. Electricity, electrical current, involves the steady flow of charged particles, electrons. If electrons are constantly moving, you have electricity. Here's a picture. Imagine that you want to have a light bulb get lit up by a battery. If the electrons can constantly go in a path around and around and around and just keep going in a loop, we call that a circuit, a complete path. That's electricity. Whereas, let's say I just remove the wire right here. The electrons are going to want to try to go this way here, but then as soon as I have a gap right here, well, then the electrons have to stop and we can't go anymore. It's kind of like how a fuse works, right? As soon as the fuse burns out, then the circuit gets broken. Okay. That's electricity. So, static electricity, a one-time zap or a buildup of charge. Well, even this one right here, I'm not even sure this would be static electricity. Does that make sense? This is just an example of how you could break electricity. Right? For it to be static electricity, you build up charge and you just leave it there, and eventually it zaps away, but you're done. Like one time, right? Like lightning. Lightning, zap, it's done. But a current, I can keep drawing it going in circles. So if this were connected, then I'd say it's electricity. Okay. So in terms of terminology, I need you guys to know a couple of words. Okay. The words that we're going to use are: you need to have a conductor, you need to have an energy source, and you need to have a load. Those are the three words I need you to know: conductor, energy source, and load. And we've already talked about conductors. Conductors are things that conduct electricity because their electrons can flow. If electrons can flow nicely, it can conduct electricity. I think an energy source also kind of makes sense. It's pretty intuitive. Like, you're talking a battery or a power plant or something. The word you probably don't know is the word load. Okay? A load is a device that does something with electricity. Okay? I don't know what it's going to do, but it's going to do that work. Remember how energy is the ability to do work? The load is going to accomplish something. Like, for example, it could be a speaker. The point of a speaker is to make sound. Or it could be a light bulb. The point of a light bulb is to make light. Or it could be a fan. The point of a fan is to create mechanical energy and create motion. Okay? So a load can be anything. A load is just like whatever you do with your device. So I found this picture online here. This is a power source, a battery. And what's happening is the electrons are going to go through the battery. They're going to go through the load. And then they're going to come back again. And they're going to keep cycling over and over and over again. What happens if this fuse breaks? Well, all of a sudden, it breaks the circuit, and then the electricity stops. And so then you don't have electricity anymore. So, now finally to the point of my lesson. The whole point of today was to teach you how to measure electricity. So now that we know what electricity hopefully is or isn't, if you get the idea of what electricity is supposed to be, we have to find a way to measure it. And there's two common ways of measuring it. One is known as its current. The other one is known as its voltage. And I like to use analogies to help describe this one. So I'm going to use the analogy of the hallway. Okay. You guys have lockers down this hallway, right? So you kind of imagine this hallway right here. Most of you guys have lockers down this way. Some of you do, at least. Okay. Imagine that I asked you to try to get from my classroom here down to the office right now. Would it be easy for you to walk through that hallway? Sure. But let me change the scenario. What if that hallway, what if it was the hallway right at 12:15, there's a huge number of kids in the hallway, there's the big lineup for the pizza line. Is it as easy to get through the hallway? But sometimes you have to maybe walk single file. Like if I had to walk down this hallway right now with 5 other people, we could just walk wherever we wanted, right? But let's say that there were a whole bunch of other kids in the hallway and you had to walk single file. It makes it a little bit harder to move. Does that make sense? Well, we have that same concept in electricity, because sometimes the electrons, they move really easily because they're in conductors. Sometimes they move, but it's a little bit more challenging because it doesn't conduct quite as well. And so using that analogy, I want to talk about something called current. Okay? When you have, I need a pen here. Actually, we'll use a highlighter. When more electrons are moving, you have more current. So again, use that analogy here. Let's say that I wanted all of you guys to walk down that hallway right now. I think you'd have no problem fitting down that hallway. But what if I were to narrow the hallway? What if I were to make the hallway be only this wide? Would it be as easy for you guys to get down the hallway? No, it would be harder, which means that in the same kind of idea of electrons, there'd be more, the word we use is resistance. It's harder to get down the hallway. I've got a picture here of different types of wires. Sometimes in the electricity, like like an electrician, they would talk about a gauge of wires. You guys ever heard of a gauged wire before? Okay. Like, say, for example, 14 gauge wire. I know it's the biggest number, but 14 gauge wire is actually the smallest. It's a very thin wire. If you had to have electrons flow in this wire, it's actually very narrow. It'd be very challenging for them to flow through this wire. But then take a 6 gauge wire. Can you see how a 6 gauge wire is really like a whole bunch of wires all looped together? It would be easier for the electrons to flow through this wire. A 3/0 gauge wire, a 3/0 gauge wire, it would actually be the easiest to flow through. Let me use that same analogy of the hallway then. If I asked you to squeeze down a hallway that was this wide, you could probably do it. It would be challenging. If I gave you a hallway that was this wide, you could probably fit about 2 people side by side. But if I gave you a hallway that was really, really, really wide, more people could flow through it. Does that make sense? That's current. Current is like how much you can fit in your wire. Okay? So because this one is so narrow, it has a high resistance. Whereas this one right here is so wide, you can fit more. So more electrons moving, more kids moving in the hallway, the more current there is. Okay. Now the other way that we measure electricity is in something called voltage. Voltage is how much energy they have. Okay. Current is how much can fit, but voltage is how much energy they have. Okay. I want to give that same analogy here. Imagine you wanted to go down the hallway here, but rather than it being you walking, I want you to be pushed by your friend on like a rolly chair. So, do a silly little example here. Okay. So let's say I want to get from here to there. Is anything in my way? Do I have any issues kind of traveling that direction there? Okay, so that means I probably have a high current. There's nothing in my way. Now if I push like this, that's like a little bit of voltage. I'm moving slowly. I didn't give myself a lot of energy. I hope I don't break my desk. But if I push like this, that's more voltage. Does that make sense? Voltage is how much energy you give yourself. As I break my desk here. So the width of the hallway means that more people can fit. That's current. The more that can fit through the wire, that's your current. But the faster they move or the more energy they come with, that's your voltage. And we call voltage by a few different names. Sometimes we call it a potential difference. Because really what it is, it's the difference in energy between the start and end of their journey. If you give it more of a push, more of an oomph, it has more voltage. Okay. I got a picture on here again of your wires. Remember how there was the hot wire, the neutral wire, and the ground wire? Electricity is supposed to go through the hot wire to the device and come back to the neutral wire. Well, if you have a device that's like, say, a 120 volt device, it means that it's giving it that much of an oomph to get it pushed, because it has to go through the hot wire to the device and back again. You better give it a good push, because the electrons have to get all the way through and back. Does that make sense? If I only had, like, say, 10 volts, the electrons might only make it that far, and then they'd stop because they ran out of energy. Does that make sense? So you have to have enough voltage to be able to force the electrons to go all the way around with enough speed. Voltage is like the energy boost you give them. Current is how many of them there are. So if you have a thicker wire, you can have more electrons flow. They might not be flowing fast, but you can have more of them. I have another analogy that I use here. It's actually of a water tower. Sometimes this one helps with kids too. Imagine that there was a water tower sitting way up high, okay? And the water in the water tower, let's pretend those are electrons. Here's what I want to do. I want to put a little leak in the bottom of the water tower right here. Just a little leak. And it's just going to drip. Like drip, 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 drip. If it's just dripping, just barely, that means there's not a lot of current because not a lot of stuff is actually flowing. Does that make sense? Like if it was just a small leak, you'd have a small amount of current. Right, Riley? Are you listening? Okay, guys, I'm getting close to the point where I'm just going to start sending kids out of the classroom. Okay, give me your attention. If there was just a small leak, that would be a small amount of current. But what happens if like the hole that it was like leaking through, what if it was a pretty big hole and water was like gushing out the side? Well, that would mean there's more current because more of it is actually moving. Okay, current is about how much actually flows. Now, voltage is about your energy. In this example right here, imagine that the water tower fell this distance right here. What happens if I built the water tower and the water tower was only like, say, this high above the ground and it only fell that distance? Which would have more energy by the time it was done? Well, the taller one, right? If I use that same example right here, if I drop something from here, it had that amount of energy. But if I drop it from here, it had way more energy to it. Does that make sense? In both cases, I dropped one eraser. Okay? So if I can give some more analogies here, let's pretend that these are electrons. Okay? This would be high current, high voltage. Lots of them fell from a long distance. This would be low current, high voltage. They fell really far, but there were only two of them. Does that make sense? This would be high current, but low voltage. Lots of them fell, but they only fell that far. And then this would be low current, because there's two of them, low voltage. You guys feel like you get that analogy there? Current is how much, voltage is how much of an oomph you give to it. Okay? Once you get the idea of how these things work, then the last thing I got to show you is some math formulas. And I asked you guys to bring calculators, because I got to show you how to do a couple of math equations. So if you have a calculator, use it. If not, use your cell phone, I guess. Okay. Before I get to the formulas we're going to use, though, I should tell you the devices we use, because this comes up here. If you want to measure current, current is measured in amps, and so we use a device called an ammeter. And the way you'll know that it's an ammeter is that you'll see this device, and it'll have a little A on it. A is for amps, and amps is how much current you have. So if I drop 5 markers, I have 5 amps. If I drop 1 marker, I have 1 amp. Okay? So, now if you want to measure voltage, you use something called a voltmeter. Makes sense? Voltage makes voltmeters. You'll see a V on it. A voltmeter then doesn't measure how much you have. A voltmeter measures how much energy they had. So that's, again, whether I dropped it from here or from here. The more energy, the more boost I give it, the more voltage there is. There is also such a device called a multimeter. It actually makes sense the way you describe it. A multimeter, more than one, it measures everything. So the way this device right here works is it actually can measure current or voltage or other things even. So I need you guys to know these words here. If you ever come across the word galvanometer, by the way, it's another fancy word for ammeter. So either of these two things can measure current, and then a voltmeter measures voltage, and a multimeter measures like everything. All right, so here's kind of the main point of our lesson now in terms of measuring this. Okay, I need you guys to be able to do some math calculations. And the formula we're going to use is something called Ohm's law. What Ohm discovered back in 1826 is there's actually a relationship between your voltage, which is measured in V, and your current. The letter we use for current is I, by the way. I don't know why they picked I, but current is measured in the symbol I. Okay, I found this picture. I hope this kind of makes sense here. Oh, my board is glitching out on me here. Come on. It's called Ohm's law. Not Oma. Oma is my grandma. Ohm is something different. So here's how this works. Imagine this picture right here. Volts is what gives you that energy to move. It's what gives you that push. Amps is how much you're trying to fit. But the other key thing here is known as an ohm. Ohm is known as resistance. Remember that analogy of the hallway I gave you earlier? If all of the grade 6s are in the hallway and you need to get from here to there, there's a lot of resistance in your way. There's a lot of stuff blocking you. And that's the relationship, is that this gives you the push. This is like how much you're moving, but this is trying to prevent you. It's in your way. And so we actually have a way of trying to put all three of these variables together. The formula is this. It's Ohm's law. It's R equals V over I. If any of you guys have your old chemistry sheets nearby, this is actually one of the formulas written on the back of the chemistry sheet. And you'll get this when you write your PAT. You have it nearby, Esther? It's the R equals V over I. That's the top one, right? Perfect. Okay. Now, what I might recommend you guys do is if you have your formula sheets nearby, you may want to write some of the other formulas that are similar. I've actually got them on this slide right here. If you know your algebra, because you need to have a little bit of math background here are some alternate formulas where you do like some algebra to rearrange them. Courtney. Did you do this one here? Yeah, so like if you're looking for current, then you cover current and it's V over R. Or if you're looking for resistance, it's V over I. Or if you're looking for voltage, it's R times I. Yeah, that's a great method here. If not, though, I need you to write these ones down so that you know which formula to use. So the last thing we're going to do then is we're going to do a couple of their math equations, basically. So let's try one here. Let's say that you connect your electric stove, which is 240 volts, and you use an element which is 20 amps. My question is, how much resistance was there slowing it down? So here's what I do first. Let's draw that triangle again. It's a V over R times I. And what we want to do is we want to figure out which one we're looking for. So if we're looking for the resistance, if you kind of cover the resistance, the formula for resistance is voltage divided by current. All you need is a really basic calculator then. Your voltage was 240 volts. Your current was 20 amps. So if you've got a cell phone or a calculator or something nearby, what's 240 divided by 20? Perfect. Now, whenever we measure something in resistance, the unit for resistance is called an ohm, and it's like this horseshoe shape. It's actually the Greek letter omega. If you know your Greek alphabet by any chance, like alpha, beta, gamma, delta. Oh yeah, totally learned that. Anyways, if you've ever seen it before, it's this horseshoe shape. It's called an ohm. It's the unit we use to measure resistance. So the more ohms you have, the more stuff is in your way slowing you down. Using that same analogy of the hallway, right now there's nobody in the hallway. There's no resistance. Put 60 grade 6s in the hallway and try to get down the hallway, it's a little harder. You got to kind of weave your way through. I guess. Yeah. You guys get what I'm saying here though, right? The more stuff in your way, the more resistance there is. I'd like to try one more example here, because I only had one example here, but I'd like to try another one with you guys. Let's say that you had, guys, give me one last example, would you? Let's say that you had 10 ohms. And let's say that you had 15 amps of current. So this would be your resistance. This would be your current. If I asked you to solve for the voltage, this is the sort of question I might ask you. I'm going to give you a resistance. I'm going to give you a current, find the voltage. So here's how you'd solve this. Again, you need to know your formula. It was V, R, and I. If you're looking for your voltage, then your voltage is your resistance times your current. Yeah, you're way ahead of me here, Ryan. The reason why is that your resistance was 10. Your current was 15. So then 10 times 15 is 150. And the unit we would use is voltage is measured in volts. So current is measured in amps, voltage is measured in volts, and resistance is measured in ohms, which is like the horseshoe shaped thing. Okay, it's very basic, but I really recommend you guys want to practice this a little bit, okay? Because it does involve a little bit of math skills. And I know that not everybody is maybe as comfortable doing math and algebra as others. So if I could, I want to end our lesson then with one more example off of our assignment, and then I'm going to give you guys 20 minutes to work. So if you have your assignment nearby, I want to hop down. I want to try number 12A. I will do this question with you guys. Number 12A. No, you don't have the same ones. I think so, yeah. So here's the question. Let's say that you have a 12-volt battery and you have a 15-ohm resistor. We want to look for current. Because I'm actually even doing your assignment for you, so you may as well write this one down. I'm going to do 12A. I'm going to ask for the current that goes through a 12-volt, 30-volt battery if there's a 15-ohm resistor. So again, you just need to know your formula. It was V over Ri. And I'm asking you in this example here to find me current. Which letter do we give current? Okay. So if it's I, get rid of the I right here. The formula is voltage over resistance. In this example right here, the voltage was 30 volts. The resistance, I believe it said, was 15 ohms. Yeah, I'm not even sure you need a calculator for this one. But if you do, you need 30 divided by 15. 2. One more thing, though. You should tell me what unit it is in. Current is measured in A, which is known as an amp. 2 amps, by the way, is more than enough to be dangerous to a person. Remember, like, I think it was 0.1 amps is enough to be actually dangerous. So you actually, like, we got to be careful around a lot of electrical circuits, because if it has a high enough current, it can be dangerous. Well, it depends on the resistance. So the voltage was 120 volts, because that's what a voltage is. So it depends on how much resistance your body provided. Does that make sense? So I don't actually know what human body resistance is. Yeah. So I mean, so long as it was like, say, 100 ohms, then it would be 120 divided by 100. Yeah. Voltage is V. Yeah. So this is V for voltage, and that's horseshoe for ohms. Right. MA? Good question here. Guys, listen to this one here. Ryan asked a good question here. If I give you MA, that stands for milliamps. You guys have heard of like millimeters or... So if you ever get a milli something, the way you deal with a milli is that you divide by 1,000. Okay. If you ever have a milli something, it means it's 1,000 times smaller. Okay. So if I were to give you on this question right here, 625 milliamps, you actually have to divide it by 1,000. Then you have an amp. That's a great question, Ryan. Okay, let's do a summary of what we learned today. I think I can break it up into about 3 main things. The first thing that we talked about is how charges work. Okay, how do you make something negatively charged? Add electrons. How do you make something positively charged? Remove electrons, yeah. Right? And usually we can do that through like friction, by like rubbing the metal rod and the fur together. Here, this guy right here is going to be gaining electrons, and this guy's losing them. He has lots, though. Don't worry. The fur has lots of electrons. Okay. Now, when we use something like that, we can then see separation of charge. When I bring this nearby, it's actually causing all of the electrons to go down to the bottom and the positives to the top. That was induction. But if I touch it, it actually transfers those electrons. That's one thing we learned about. Induction and conduction and separation of charges. The second thing we talked about was static electricity versus electrical current. Static electricity is a one-time buildup of charge, and you could get zapped by it, but once you get zapped, it's done. Does that make sense? Whereas electricity, electrical current, keeps going through a loop over and over and over again. And if you ever break the loop, the electricity turns off, right? When I turn off the light switch, it breaks the circuit, the lights go off. Okay? The third thing we learned about is how to measure electricity. The 2 main things you need to know are current and voltage. Current is how much you have. When I dropped 5 pens, that might be 5 amps. If I drop 1 pen, it's 1 amp. But voltage is how much energy you give it. So if I drop it from up here, that might be 10 volts. If I drop it from down here, that might be 2 volts. So there's how much, and then there's also the energy you give it. They're linked by something called the resistance. Resistance is what slows you down. The more resistance you have, the less that can move. Okay, and so that final thought then is you need to be able to use this formula here, the one that's on your formula sheet, which is this one here, R equals V over I. If you can use that formula and do some of the math equations, you're doing great. Okay, any questions, comments, concerns, conundrums, curiosities, complaints, criticisms, queries? A conundrum? Oh, I know. These are just questions. Okay, guys, one last piece of advice and I'm done. Okay, you have 15 minutes left, okay? The tendency for some kids, I know you guys, a lot of you had this problem when I taught you chemistry, is to just be like 15 minutes, I'm going to pack up. Here's the advice I'd give you, though. Do a couple of questions here. Like, for example, here. Can you tell me what a voltmeter and an ammeter is for? We just talked about it. Right? Do these questions while they're fresh in your mind, okay? If you were to do 15 minutes a day, you will finish this assignment in three days. Okay? But if you try to do it all at once, it's so much more work. McKinley. Okay. Okay, I can do that again. How about this? How about I just come talk with you, though? Does that work? Okay. Guys, you have 20 minutes, okay? Maybe 15 minutes. Don't waste it, okay? Yeah, you have 15 minutes, okay? Use it well, okay?